Okay, hello everybody. Back again to our statistics course. We have some exercises left and we want to start with the next one. Yesterday we talked about, in general, averaging data and that you have to keep in mind to use the right average and that sometimes the arithmetic mean is not the best choice. On the other way around, and this is then the next exercise, number 4, is that we see that the arithmetic mean is therefore mostly considered when we are averaging data because this average has actually some really nice properties. And I don't know if you have talked about these properties in your introductory courses. I think it is important to know why. The arithmetic mean is not only intuitively the first thing we would think about by averaging data, but also that it has some theoretical, really nice um, properties, that it's also reasonable always to think, is the arithmetic mean not, in my case, a good choice for averaging data? Okay, so then let's take this and the first property is just that maybe you remember it from school, that if you have a triangle and going from every side to half, that these three lines are crossing in one point, and if you put your finger at this point in the under the triangle, then the triangle is just sitting on your finger. Yeah, because this point is just the center of mass, which you find via this geometric construction. And yeah, so to speak, you can also think if you have data, then you have many, many data points. And this form also something like an area. And then also calculating the arithmetic mean just means that you then create with this arithmetic mean a new data point, an average data point, and this is physically spoken the center of mass of your total data. And this is this first property, that if you sum up all difference with respect to the arithmetic mean, and you do not take as an mean absolute deviation or variance squaring these differences, if you just say also, yeah, it can be possible that data which is higher than the arithmetic mean and which is lower, that these two numbers can cancel out, that if you take every difference and summing this up, then every distances in the end cancels out. So see, geometrically spoken, the arithmetic mean is the center of mass or the center of your data in a theoretical way. And then let's show this. So if we write down from I to n, oops, now my Zoom meeting is canceling. Let's see. Oh, have I started the recording? Yeah. Anyhow, since nobody was entering, I think, then let's just skip the Zoom meeting. Okay, so xi minus x bar. So now we have to show that this is 0. Well, and for this, you have to know how to calculate with this summation operator. And do you remember it from school or from your math course? What can you do now? So this summation operator, sum over xi, to, let's say, 3, and if x1 is 1, x2 is 4, and x3 would be 5, then this just means 1 plus 4 plus 5 is 10. This is only just a writing that you do not have to always write down all your data points. Well, and for this, we can also ask what is then xi minus 3, I from 1 to 3. If you write down this, then you have always to subtract 3 from your numbers. So this is then 1 minus 3 plus 4 minus 3 plus 5 minus 3. Well, and then you see here is the same summation process as you find it above. So you can write this also as 1 from 1 to 3 xi minus sum over 3 from 1 to 3. So this you can write then as 1 plus 4 plus 5 minus opening brackets. Well, and then you have 3, 3, and 3. So 3 plus 3 plus 3. So this is then one special example, and this you have to keep then for this general purpose, because there we want to show this independently of that we are know all specific numbers. So we can split now the summation into I equals 1 up to 3 xi minus x bar I from 1, not 3, but n, sorry. Oh, sorry. And, well, this is a fixed number. This is could be, as in our example, our 3 in our simple example here. Any number, but it is fixed. So if this number, this fixed number is sum up from 1 to n, what can we write then for this? Well, here from 1 to 3, we had to sum up 3 times the number 3. If we sum up until an index n, then this n could be 7, 1,455,000. So we have to sum n times our arithmetic mean. So this is then n times x bar, like you have it here. 3 times, and then we had this number here. 3 plus 3 plus 3 is 9. Okay? Then we write down here. Here we cannot do anything else. Minus n times x bar. Well, and now we feed in just the definition of x bar. X bar is the sum of all our data points, xi, divided by the amount of our data set. So this is then sum I equals 1 to n xi minus n times 1 over n sum over xr, because this is just arithmetic mean x bar. Well, and then you see that the n cancels out. And then you have sum over all data points minus sum over all data points, and this is of course 0. And in former times, I know that unfortunately in school we are not definitely show anything anymore, but if you have shown something, then you in ancient times you have written quod erat demonstrandum. I don't know if you have seen this in school. But this should then show that you definitely have shown this property of the arithmetic mean. Well, then let's take B, that we have, if we transform our data in a linear way with some numbers A and B, as we have done it, or as I have shown you when we were talking about in general about expected value, that this, if we manipulate our data linearly, that this also only shifts our arithmetic mean in the same way. Well, in economics, you do it quite often. Think, for example, if you change the currency. Change in currency just means that you manipulate your data by multiplying with some number. So then let's write it down. Sum over xi prime, I from 1 to n. Then we just write into our summation sign these linear transformation, the definition of xi prime, sum over xi times a plus b, I from 1 to n. Then again, we know that we can split as we did it here, sum over this, sum over this. So this is a times xi, I from 1 to n plus sum over I to 1 to n. This is again only a fixed number. This is a fixed number. Well, there, if we think here in front of this, let's take another color, would be a 4. Then this would mean we had 4 times 1 plus 4 times 4 times 4 times 5. This is then 4 times 10. And this, of course, can also be written as 4 times, opening brackets, 1 plus 4 plus 5. So what we can do is we can just put out the constant number in front of our summation sign. So what we obtain, take black again, equals a sum a1 to n xi plus n times b, because b is again this fixed number. Well, and this is the sum over all of all our data points. So this is just n times x bar. So then we obtain n times x bar plus n times b. Then we can take out the n. So this is a x bar plus b. But this is again x I prime bar. Or what we also can do is, and let's take this again in red, just write in front of this always 1 over n, 1 over n, 1 over n, 1 over n, 1 over n. So this is xi x prime bar, sorry. So there are also no I there, only x bar. And then you see this n and n cancels, and you have then that x bar prime equals a plus x bar plus b. So a linear transformation of all data points also shifts the arithmetic mean with the same linear transformation. And then maybe the most important property, and this is number C, that we can think of in general any average of our data points. Well, and then we can show that the arithmetic mean has one really special property, that the sum of all squared distances with respect to the arithmetic mean is the lowest sum we can obtain. Well, and this is then we talked a little bit already about the reasons why we are using quite often in statistics the square distance. Well, and then it seems reasonable if we want to aggregate in order to describe volatility of our data with the squared distances with respect to some average, that we then take the average for the averaging process, the average which guarantees us the lowest dispersion of our data. And this we also want to show. Well, and for this, we can start with this part. I equals 1 to n xi minus m squared. And then it's a trick which we use in mathematics quite often, is to multiply anything with a sophisticated one, or we add our mathematical term with some sophisticated zero, because then we are changing nothing. If we add in this part plus zero, then nothing changed and we can still use our equality sign. And what do? We insert a zero via the following process: xi minus x bar plus x bar minus m squared. So we just inserted here the number 0, so nothing changed. Well, and then let's say that we interpret this as A and this as B. And hopefully you know still what is A plus B squared. These are your binomial formulas. I think class 9 or something in school. The first binomial formula is, yep, c squared. Now you are thinking about the Pythagorean theorem, rectangular triangles or something. So if you just multiply this, a plus b times a plus b equals then a squared plus 2ab plus b squared. Okay? So, and this, since we have here these squared, we take just, so sum over 1 to n equals then the first term, a squared is xi minus x bar squared. Now 2 times a and b, so plus 2 times a xi minus x bar minus m plus b squared, so x bar minus m squared. Well, now we have again to remember our summation operators. Since we have here always only a plus sign, we can move this summation operator to every part of our sum. And what we see here, this is again only a fixed number. And this is, of course, also only a fixed number. And we know n times summing up a fixed number from 1 to n is just n times the fixed number itself. So this part is then n times x bar minus m squared. In the second term, here you have the I. We don't know what are our data points. We know only this is a general data set. So there we still need our summation sign, but since this here is a fixed number, this we can take out of the summation sign. So we obtain 2 times x bar minus m times sum over x bar minus xi from 1 to n. Plus, and well, in the first term we cannot change anything because we have here also the square. I from 1 to n xi minus x bar squared. So this here, if we go to our page for 10 minutes ago, this is just the property of A that we know that the sum of all distances with respect to the arithmetic mean just cancels. So every distance is cancels out. So, oops, this is just 0 from property A. So here we have n times x bar minus m squared. What sign has this number? Is it positive or negative? Think of n is 17, x bar is 12, and m is 100. 12 minus 100 squared is positive or negative? It has to be positive, and it has always to be positive. If we are squaring something, it is only in the minimum 0, but then m has to be x bar itself. In all other cases, this is positive number. So since, or this is a positive number. But what have we seen here? We see then that the square distances with respect to any possible number is equal to the square distances with respect to the arithmetic mean plus some positive number. So this means that this always has to be larger than this part, because we have here this equality sign. So let's write it down. Then sum over sum over in xi minus m squared is I1n in x bar plus n times x bar minus m squared, and this is positive. Then we know that the squared distances with respect to any number m has to be larger than the squared distances with respect to x bar. So in the end, sum over xi minus x bar squared I from 1 to n is always less to sum xi minus m squared I from 1 to n. So, and one last theoretical thing I wanted to show you, I think. Too much. This one and this one. So, because I introduced for you the so-called unbiased variance. Well, and I think in most courses it is only told you that, well, there is some correction factor or so. And I want to show you, since we are in a somehow advanced course, why is this a reliable correction factor which we have? Well, what we want to do with our estimators, well, we want on average describe our data set. Well, and then we want to make some conclusions from our data sets to the general distribution. And for this, if it's possible, we want to calculate our estimators in such a way, oh, there's a square missing, that on average, or that the expectation value of our estimator equals the true parameter. And for this, we now show that if we calculate the variance with this correction factor 1 over n minus 1, that surprisingly then our estimator, the expectation value of our estimator equals the true parameter itself. Well, and in order to show this, we just calculate our expectation value of our estimator. Setting in the definition is expectation value sum over n minus 1, I from 1 to n, x I minus x bar squared. Well, in the following, I skip the summation from 1 to n in order that I do not have to write that much, okay? These two, this and this, I skip in the following. I do not write it down anymore, but we know that we are summing up from 1 to n. Well, this is a fixed number. We talked about in the beginning of the lecture also that the expectation operator is also a linear operator, so a fixed number can be taken out. So this is then 1 over n minus 1 e I from 1 to n xi minus x bar squared. Oh, I wanted to skip this in the next one. Well, and now again we make the same trick as before, where we inserted a practical zero, and this we do now too. So 1 over n minus 1 expectation operator sum over xi, and now we take the expected value. We don't know, but we know there is in general the expected value of our data points, mu minus mu plus mu minus x bar squared, closing brackets. Again, taking the binomial distribution. Oh, here's a bracket missing. Thinking of this is A and this is B. We obtain 1 over n minus 1 e times the sum xi minus mu squared plus, and now since we know a squared plus 2ab plus b squared, we can just put in front of every term our summation sign. I will do this right now. This is again as x bar minus m in the former example a fixed number. This can be taken out of the summation process. So we obtain mu minus x bar times sum a xi minus mu, and summing up n time from 1 to n, a fixed number. This is just a fixed number. We obtain plus n times mu minus x bar squared. Well, what do we have here? let's just look only at this part, minus mu. This we can also split, equals sum over xi minus sum over mu, but this is nothing else than n times our arithmetic mean. So n times x bar. This is from I to 1, sum over a fixed number is also n times mu. Taking n out, we obtain n times x bar minus mu. So then, for this, since we know that this here equals this, we obtain n times mu minus x bar times x bar minus mu. Then we write down this x bar squared and sum over xi minus mu squared e and 1 over n minus e plus and oh sorry, here a 2 is missing because we have a squared plus 2 times a times b plus b squared. So here's also a 2. So what do we see? 1 over n minus 1 times e of sum xi minus mu squared. Well, here we have mu times minus x bar times x bar minus u. So in brackets are almost the same numbers, only with a minus sign. Okay? So this is then nothing else like minus 2n times mu minus x bar. So this is nothing else like mu minus x bar squared. There's one bar, this one. Okay, do you see this? Well, then we have, oh sorry, oops. Then we have here and here the same numbers. But here we have the 2, so minus 2, so only 1 times n minus mu minus x bar squared is left. So then we obtain that minus n times mu minus x bar squared in brackets. So now we are almost done. But what do we have here? This is just the definition of our variance. All data points with respect to the expected value squared summed up. So this is n times sigma squared. And here we have 1 over n minus 1 e of n minus sigma squared. Well, but here we have the difference between x bar and mu. But what is this? This is nothing else than the variance of our arithmetic mean. So this is x bar squared. So, and what do you know, hopefully from your introductory statistics courses, is that the variance of your average is scaling with the number of your data points. So this is nothing else than the variance of our sample divided by n. So remember, variance of the mean x bar is scaling with 1 over n, the number of the sample. Well, this is the reason why you are not only asking 100 people, but 1,000 people, because then you know that your variance is in general narrowing. Well, and if we insert this, then we obtain n times sigma squared over n expected value, and then 1 over n minus 1 e of this cancels out, sigma squared times n minus 1. And now we have here only fixed numbers, and the expected value of a fixed number is just a fixed number. So 1 over n minus 1 times sigma squared n minus 1, and this cancels, and we obtain only sigma squared. And now you can look at from this to this, and then we have shown this property that the expected value of our variance defined with this correction factor n minus 1 equals the variance itself. Well, and maybe the important things is just the manipulation at this point you have to see, and is then this scaling property. also QE. Okay, but that it was at first for the theoretical explanations, and I think some other, but yeah, 6, 7, and for 7 I have to look up because the Bundesbank has changed their statistical data set if I find the DAX data. I think in Google Finance or Yahoo Finance I should find it. Have you already worked with Google Finance or Yahoo Finance or something? Or you're studying tourism or okay. Okay, then next week on Monday we will do this and then we will start with the linear regression. Thank you very much.